So we have completed 3 modules of our course. First, divide and conquer. Second, greedy algorithms. And third, dynamic programming. Now we'll start a new module, network flow algorithms. So today we'll define network flow algorithms. Yes. So network flow problem we will define, and today we will design an algorithm so for solving the maximum flow problem for Fulkerson algorithm, and we will derive its time complexity. And next lecture we will prove its optimality using a theorem, maximum flow minimum cut theorem. Then we will have 2 applications of this algorithm, bipartite matching and computing the number of disjoint paths in graphs. So today we'll define maximum flow problem and design Ford-Fulkerson algorithm. So first we define flow network. So flow network, we can define it as a directed graph. So first we have a directed graph. Let G be VE. V is the set of vertices, E is the set of edges. So it should satisfy 4 properties. So first is, so for each edge we have a capacity. Each edge. So just remember, edge is a directed edge. E has a capacity. We denote this by CE, and this is non-negative integer. Non-negative integer. Yes, weight. Second, we have a source, S in V. This is a source node. So property of the source node is no edge enters. So just in the diagram format, this is not allowed. No edge enters S. Yes, you can say that in degree of S is 0. Similarly, we have a sink node, call it T. T is in V, this is called sink node. This is just opposite of the source node. No outgoing edge is allowed. So no edge leaves T, or in short you can say out degree of T is 0. Out degree of T is 0. Then other nodes are internal nodes, remaining nodes. We can say STU for all V U belonging to V minus ST. So these are internal nodes. And one more property, there is at least one edge incident to each node. At least one edge incident to each node. So this incident means either coming to or going out. So these 4 requirements are there for a directed graph V E together with a set of capacities to be called a flow network. 4 properties. First, each edge has a capacity. We have 2 distinguished nodes, source node with in degree 0 sink node without degree 0 and all other nodes with at least one edge incident on it. One? Yes, yes, one, single. So I have written here S and T, single source, single sink. So very simple example of a flow network, S, U, V and T. We have directed edges like this with capacities 20, 10, 30, 10, 20. This is an example and we'll take this for describing the algorithms. Next we define a flow, ST flow. ST flow we define. So this is a function f from the set of edges to positive real numbers. So Fe for an edge, we can say this represents amount of flow. This is equal to, we can say, amount of flow carried by edge E. So two conditions for flow we should have: capacity and conservation conditions. So capacity condition says that flow cannot exceed the capacity. So first we have capacity conditions. This says for all edge, this flow should lie between 0 and the capacity. This is capacity condition. Flow cannot exceed the capacity. Second is conservation condition. So source node is the generator of flow, sink node is consumer of the flow, and remaining nodes, they conserve the flow, means they cannot absorb flow or cannot generate flow. So they should conserve, means inflow should be equal to outflow. These are called conservation conditions. Second, conservation conditions for other nodes than source and sink. So for all V belonging to V minus source or sink, we should have inflow equal to outflow. So inflow we write sum of all Fe, the edge into V, incoming edge to V. This should be same as flow out, Fe E out of V. This is conservation condition. So once again we take the same example and take an example flow. So taking the same figure, here we have a flow network. Now we define a flow satisfying these properties. So along this edge we have a flow of 20. Just writing like this, F is equal to 20. Along this edge we have flow 0. Flow is 0. Along this edge we have flow equal to 0. Flow is 0 here. Along this edge we have flow equal to 20. Flow is 20. And along this edge we have flow is 20. Now, yes. Flow? Yes, it is different. Flow is different. So flow is a function of the edge. It is different from the capacity. So now we should
So the weights that you mentioned earlier were the capacity.
Yes, capacity. So this is property of this graph. Weights are property of this graph. The capacities. Flow is a function on edge. You can vary flow. but for a graph capacities are fixed. So now we should verify the two conditions. First, capacity condition, you can easily see flow is 20, capacity is 20. Here 0 and 10, flow is 0, capacity is 10. Flow is 20, capacity is 30. Flow is 0, capacity is 10. Flow is 20, capacity is 20. So capacity conditions are satisfied. Next we should verify conservation condition. So the only two nodes are U and V other than S and T. So for U, incoming flow is 20, outgoing flow is this 0 plus 20, 20. So flow is conserved at U. Similarly at V, incoming flow 0 plus 20 is 20, outgoing flow is 20. Again here also satisfied. So this is example of a flow. Next we define flow generated by the source. So value of the flow Vf equal to, so just remember this V is different, just do not confuse it with the vertex V. Here V means value of the flow, value of flow. So this is simply the flow generated at the source. So Vf we define as sum of all Fe E out of S, E out of S. So how much flow the source is generating. This is definition of value of the flow. So once again we take the same example and compute how much flow is generated by S. So outgoing flow from S are 20 and 0. 20 plus 0 is 20. So for this flow we have Vf is equal to 20. This is, so Vf is sum of all Fe E out of S. Outgoing edges, compute F flow. Yes, outgoing edges, F of E, where E comes out of S, outgoing edge from S. Yes, once again you can see, just make a boundary around S, see outgoing edges, compute the flow, add them, we get 20. Now same way for conservation condition also, we can define flow out and flow in, and they should be same. So similarly we define, this was value of the flow, flow out of S. Same way we can generalize this to any other node. So we write F out of some vertex V. So again simply sum of all Fe E out of V, E out of V. So this is flow out of V. Similarly we can define flow into V, just opposite, flow in V, sum of all E into V, E into V, Fe. Now same way we can also generalize this to any set, flow out and flow in. So taking any subset S of V, we define F out of S. So again same idea, just make a boundary around the subset S, see what are the edges which are crossing it, which are going out of S. So sum of all Fe E out of S. Same way we can define F in of S, flow coming in S. Just opposite, F in of S is sum of all E into S Fe. Now conservation condition, take any vertex, flow in should be same as flow out. So we write this as conservation condition using this notation. Flow in should be equal to flow out. So f in of any vertex v should be same as f out of any vertex v for all v other than s and t, v minus st. This is conservation condition, and value of the flow Vf is f out of the source node. So using this notation f in f out, we can write value of the flow as f out of s, where s is the source node. This is small s source node, and this is any subset capital S. So just distinguish between the two. Now example we will take. In the same example, yes. So conservation condition, flow in of any node is same as flow out of any node. Value of the flow is, this is definition of value of the flow, f out of s. Now taking the same example figure this. So we have already computed flow f out of s is 20 plus 0 is 20, value of the flow is 20. Now v u, so conservation at u, again same way, just make a boundary around u. F in, so compute f in, flow into u is 20, flow out of u is, there are two edges, along this it is 0, along this it is 20, so 0 plus 20 is 20. So it is conserved. F in of u is same as f out of u. Now we define the maximum flow problem with these definitions. We define maximum flow problem. So here the input is a network flow, a flow network, not network flow, a flow network. So flow network means, as we defined earlier, it is a directed graph with set of capacities. So this is the input, output, find a maximum flow, find a flow of maximum possible value. This is the problem, maximum flow problem. Given a flow network, find a flow of maximum possible value. So to solve this problem, we define one more idea. It is of residual graph. So we define what is residual graph, and using it how we can solve this problem, and we will show you the working of Fulkerson algorithm. So now we define residual graph. So for residual graph, we are given a flow network G. So given two things should be given a first is flow network G. So this G includes the capacity also and a flow. So two things are required. First, flow network G and a flow F on G. So this F satisfies the two conditions, capacity condition and conservation condition. So this is a valid flow on G. So given these two, we define a residual graph, call it GF. Residual graph GF is defined as So this flow network G and corresponding to the flow network G and flow F, GF, how we define GF. So we define it as, now set of nodes are same. So we can say set of vertex set of GF is same as vertex set of G. There is no change in vertices, only change is in edges and their weights. So there are two types of changes. So consider any edge E equal to UV in V, on which, so consider any directed edge, this like this, U to V in G, on which we have FE. FE is less than CE. So here our observation is that we have a flow of FE and its capacity is CE. So means how much we can increase the flow. So we can increase by amount CE minus FE. So this CE minus FE amount of flow can be added along E. This is our observation. So what we do is we make a forward edge with this weight. So in GF, what we do is the same U to V with this weight CE minus FE. This is called forward edge. Forward. So this is only when FE is less than CE, how much flow we can add, extra flow, that is of amount CE minus FE. This is the weight of this edge U to V in GF and we call it forward edge. Same way, just opposite idea is of backward edge, just the reverse. Third we have, take any edge E equal to UV of G. So once again we have U to V, this is the edge, directed edge in G, and here we have FE, assuming that FE is greater than 0. So here just see the opposite, how much flow we can decrease. So we can decrease FE amount of flow. So FE amount of flow can be decreased. Yes, FE is greater than 0. So, no. So this FE, it lies between 0 and CE. These are the boundaries. If it lies strictly between them, like FE is less than CE, then we add a forward edge. How much weight? CE minus FE. And again, if it is greater than 0, so forward edge corresponds to how much flow we can add. Backward edge corresponds to how much flow we can decrease. So both we have to keep account of. So we can decrease, FE amount of flow can be decreased. So we make a backward edge. Call it E prime is equal to V to U, just opposite direction. So this is the backward edge with weight FE. So when there are boundary conditions, yes, I will give an example, you can see. So forward edge, it is of the same direction as the original graph with weight is CE minus FE, and this is only when FE is less than CE. If FE is equal to CE, then we do not make forward edge because its weight is 0, we ignore it. Similarly, backward edge, we reverse the direction, suppose, and we make only if FE is greater than 0. How much? Having weight FE. If FE is 0, we do not add backward edge. So there are, we can get two edges, forward and backward, with different weights. So now example we will take, same example. So once again I will draw the same figure we will draw and find its residual graph. So consider the same example, flow network G, S, U, V and T. Capacities are 20, 10, 30, 10, 20, and the flow is so flow I will show like this inside a circle to save space. This is the flow, 0, 20, 0 and here 20. So this is our graph G together with a flow F. So F we have defined. Now for this we will make GF, the residual graph. So just make and compare S, U, V, T. So set of nodes are identical. Now consider each edge one by one. So first we consider this edge. So its flow matches with its capacity. So we do not draw forward edge. It is greater than 0, so we add backward edge with weight 20 according to our definition. So we make a backward edge like this with, this is our GF, weight 20. Next we consider S2V edge, capacity is 10, flow is 0, it is less than CE capacity. So we make a forward edge with residual CE minus FE 10. So forward edge we make of weight 10. Now there is no backward edge because flow is 0. For 0 flow there is no backward edge. Next we consider U and U to V. So U to V we have flow 20, capacity 30. So we will have both. For forward, how much flow we can increase? It is 30 minus 10. 30 minus 20 is 10. So forward edge with weight 10 we make 10, and also backward edge with the flow 20. Next we consider U to T. So again U to T, flow is 0, capacity is 10. So we make a forward edge with weight 10. There is no backward edge because flow is 0. Last we see V to T. So V to T, flow is 20, capacity is 20. So there is no forward edge. We have backward edge of amount weight 20. So make like this. So this is one example how given a graph G and a flow F, given a flow network G and a flow F, we can compute its residual graph GF. So now what we do is we define an operation called augmenting path in a residual graph. Augmenting paths in a residual graph. So here what we do is we find a simple S to T path. So we start with a, let P be a simple S to T path in GF. Now by simple we mean no vertex should be repeated. So S to T path, no vertex is repeated. We find a simple S to T path in GF. So next we define bottleneck of path P with flow F. So we define bottleneck. Bottleneck PF. So this is equal to minimum residual capacity. So the weights in GF are called residual capacity. So the minimum residual capacity of any edge on P with respect to the flow F. So bottleneck means just follow along the path P, the ST path in the residual graph GF, and consider what is the smallest weight of any edge you get. So these weights are called in the residual graph residual capacity. So minimum residual capacity along the path P, we define it as bottleneck. So augment means we add extra amount of flow. How much? It is equal to bottleneck. So in the residual graph GF, we can add this much bottleneck amount of flow we can add. This operation is called augmentation. So we call this augment. So we define the operation augment using this. Augment FP. Here F is the flow, P is a simple ST path, and we are given this residual graph GF. So this gives a new flow, call it F prime in G. How we find it? So we have operation augment FP, and this is simple operation. Write it as augment FP. So step 1 is we find the bottleneck, call it B. Let B equal to bottleneck of the path P along this flow F. Now we consider each edge along the path one by one. For each edge UV along the path P. So there are two cases. It is a forward edge or it is a backward edge. So according to the two conditions, suppose first condition we check if E equal to UV is a forward edge. Then we increase FE in G by B. So forward edge, according to our convention, its weight corresponds to the maximum flow that we can add. So here we are just adding the bottleneck. So bottleneck can be added because B is the least weight of any edge in the path. So forward edge we increment by bottleneck, and reverse, decrease the same amount in backward edge. So else branch, else means we have backward edge. If UV is a backward edge, then let E prime equal to just call it E VU. So decrease, just the opposite, decrease FE in G by B. So according to our definition, for backward edge we can decrease the flow. So we decrease it by again the same amount bottleneck. This is a very simple procedure, and if and for, then return f. So same example we'll take and see how we can augment path. So taking the same example, GF, the same residual graph we take and augment a path S U V T. So we have this 20, 10, 10, this is 20, this is 10, this is 20. So we start with GF, the residual graph. So step 1 is we should find a path, S to T simple path. So the one that we find is SVUT, SVUT. So this path we'll find, just making this S to V, then to U, then to T. Take this path. So here we have a path S to T, simple S to T path, SVUT. So we find the bottleneck. So bottleneck is simply the least weight of any edge. So 10, 20, 10. So 10 is the bottleneck. So for this we have B equal to 10. Now we consider, yes. So this is the same GF that we have drawn earlier. So here we apply algorithm, breadth first search or depth first search you can use, starting from node S, continue until you get T. So simple linear time algorithm for finding S to T simple path. Yes, you have to find a path. Simple S to T path with no repetition of vertices. So here I have shown we have found a path SVUT. So once we find the path, we compute the bottleneck. So bottleneck is simply the minimum weight of any edge along the path. So the weights are 10, 20 and 10. So bottleneck is 10. Bottleneck is 10. Now we augment. We apply this augment operation. So we consider each edge one by one, depending upon what is the case, forward edge or backward edge. We update the weights. So first we consider S2U, S2V path, S2V edge. So this is a forward edge. So for forward edge, what we do is we increase by the bottleneck. For forward edge, increase by bottleneck, backward decrease. So we increase the flow. Yes, we increase the flow by 10. So here once again we draw this F prime on the original graph S U V T. We have this edges like this. And capacities are 20, 10, 30, 20 and 10. So for F prime, just notice that once again we have to see the previous flow. So the flow along all other edges other than the path P, they will be same. The only change will be along the path. Along the path means like this. So the remaining will be identical. The remaining are these two. So these two flows will be identical, 20 and 20. So I'm drawing them. Here 20 it will remain as such, and here also 20 it will remain. No, not graph G. We are changing in flow. Graph will be same. With capacity, the graph, there is no change in the graph G. We are changing only the flow. Residual graph also will change, but first define the flow F prime, then calculate GF prime. Stepwise we are doing. So flow we are defining. Here it says increase the flow by 10. So just increase 10. So next we have a backward edge. Backward edge, its weight is 20. So decrease 20 to 10. So 20 minus 10 is 10. So here flow we define as 10. Here flow is 10. Just write 10. So direction of the flow is same. This. Next we have this, and this is forward edge. So forward edge, just add. So flow, how much flow? So here we have decreased the flow. If you compare, just compare with earlier flow. Earlier flow was 20. We have decreased the flow from 20 to 10. We have decreased. So direction will be same. There is no change in direction of the edge in original graph G. What we have done is reduce the flow.
We decrease by 10.
Yes.
20. 10.
So
net 10
decrement. So this 20, just consider here, if the weight of the backward edge is 20, it means the flow, actual flow is 20. So we have to decrease this by 10. The result we get is 10. So flow is decreased and it is 10. So just remember this. Along backward edge we decrease the flow. Along forward edge we increase the flow by bottleneck. There is no change in direction of the flow. It will remain as such in the original graph G. So next, last edge is this, and it is a forward edge. So just increase the flow by 10. So here we get 10. So again here its capacity is 10. So we can increase by maximum amount 10. So we have increased. So this is a new flow. Call it F prime. So now for F prime, again we recompute what is the residual graph GF prime. So next we compute the residual graph GF prime for this new flow F prime. So again S U V T. So first we consider SU edge. Capacity is, flow is full. So there is no forward edge. Only we have is backward edge of amount flow 20. So make it like this, 20. Then here also same thing. Flow is full. There is no forward edge, only backward edge of cost 10. Now here, so 10, it strictly lies between capacity 30 and 0. So we have both forward as well as backward. So forward edge cost will be 30 minus 10 equal to 20. Backward will have cost 10. So make both 20 and 10. Then here also it is full. So we have only backward edge of cost 10. Backward edge of cost 10. Now finally we have Vt. Here also same thing. Flow is full. So we just make a backward edge of cos 20. Now what is value of the new flow? So Vf prime, we can easily see it has increased by the bottleneck. So just make a boundary along S. Compute what is flow out of S. So it is 20 plus 10. So new value of flow is 20 plus 10. It has increased by the bottleneck 30. So once again we apply the same idea. Try to find S to T simple path. Now you can easily see there is no S to T simple path. So here the algorithm stops. And once the algorithm stops, we get a maximum flow. So this algorithm is called Ford-Fulkerson algorithm. We start with the graph G. So Ford-Fulkerson algorithm is very simple. So we start with flow F equal to 0. Make the residual graph, find S to T path, augment by bottleneck and continue like this until we get the maximum flow. So time is over. The remaining things are we have to prove that F prime is a flow in G. This we have to prove. Then the Ford-Fulkerson algorithm, I have given the example and finding its time complexity. So I will make extra video and you can watch.